Same chapter, magnetic field, and this is lecture number 3. Suppose we have two flat circular coil current I, and this is another flat circular coil which is placed next to the first one and facing the first A and B, and both are carrying the same current I. If the distance from the center to the center x is equal to the diameter of the either coil, then definitely at the point P, magnetic field will be uniform. So I repeat, two coils A and B, flat circular coil, they are facing each other, they are connected with the same current supply, their diameter may be different, right? If the distance from center to center is equal to the diameter of either coil, then this pair of the coil is called Helmholtz coils, and they are used to produce uniform magnetic field. So here at this region, the magnetic field will be uniform, and this pair is called Helmholtz coils. Now, suppose we have a wire. It is carrying current I1. It is infinity long, and according to right-hand grip rule, this is the pattern of the magnetic field around it. This is the direction. If this point is selected for the magnetic field P, first of all, we will measure its perpendicular distance from the wire. Then according to the formula, magnetic field strength at B, magnetic flux density at P will be equal to mu naught I over 2 pi d. Now this is the strength of the magnetic field. This is the magnetic field, magnetic flux density. Now another coil or another wire is placed parallel to the first at P and carrying different current in the same direction as in the first, then the second wire, this one, will experience the force equal to BIL sine theta. Now the force experienced by this red wire is due to the magnetic field there, so we will substitute here mu naught I1 over 2 pi d. This is I1. And this current is the current of the red wire, this length of this red wire, second wire, and the sine theta. Look, this is the direction of the magnetic field, and the wire is perpendicular to the plane of the field. So this theta angle is 90 degree. So the formula is F is equal to mu naught I1 I2 over 2 pi d into L2 and sine theta 1. But the problem is this wire is parallel and it is infinity long, so we cannot measure the force due to this unknown value. So in this case, when the wire is infinity, we will measure the force per unit length for the second wire, which is mu naught I1 I2 over 2 pi d. So this is the force per unit length experienced by this red wire due to the magnetic field of this black wire. Now we have to find the direction of this force experienced by the red wire. Look, this black wire direction field is this. Mean it is horizontal, but it is vertical. It's similar to inside the board, but the wire is carrying current downward. So according to Fleming left-hand rule, field is into the page, current downward. So the force experienced by the red wire is in this direction. According to the Fleming left-hand rule, this is the direction of the force. So the current, look, feed into the page, and the current is going in this direction. So the force in this direction, like according to Fleming left-hand rule. Correct, not downward, it is upward. Okay, correct it. Now, suppose we place first the red wire, which is carrying current I2. We draw its magnetic field. This is the direction of the magnetic field according to the right-hand grip rule, and we select a point P exactly at the same distance D away from the wire red. So this is P here. Look, instead of this distance, we take this side distance. At this point, the magnetic flux density due to this red wire is mu naught I2 over 2 pi d. Now we place the black wire at this point. And it is carrying current I1 in the upward direction, same direction. So when this black wire is placed in the field of the red wire, it will experience force according to BIL sine theta. Now the force experienced by the black wire is due to the magnetic field strength of the red wire, so which is mu naught I2 over 2 pi d, and this is the current of the black wire I1, length of the black wire, and sine theta. So F is equal to mu naught I2 I1 over 2 pi d into L1, but the sine theta will be the 1. But if the wire, this black one, is infinity long, again, F divided by L, force per unit length will be determined. So mu naught I2 I1 over 2 pi d. So this is the formula. Now the direction, look, here this field is in this direction, current is upward. So according to Fleming left-hand rule, the force experienced by this black wire is in this direction. So red is experiencing force towards the left, and the right wire, this one, sorry, left wire is experiencing force towards the right. Now look at the formula, both formula, mu naught I1 I2 2 pi d and mu naught I1 I2 2 pi d. It means that both forces are equal in magnitude but opposite in direction. It means the wires are obeying Newton's third law. Every action has a reaction, equal in magnitude, opposite in direction, right? And the next kind of the force is same. Now look at the direction. This red is experiencing force in this direction, this black in this direction. So both will lean inward due to the forces. So leaning towards each other mean both are experiencing the force of attraction. So it mean when two wires are held parallel, carrying current in the same direction. Look, this is I1, this wire I2, so both will attract each other. So similar direction current parallel wire will attract, but similar stationary charges will repel. And both wires will obey Newton's third law. Action and reaction forces are equal, but opposite in direction, one towards right, other toward left. And next important, in both, mu naught constant, d constant, pi constant. So when this portion is constant, then the force per unit length in both wires directly proportional to the product of I2 and I1. So which is the evidence. So both are carrying same current or different current, but they will experience the same force. Whether the current same or not, the force depending on the product of the currents. So the both wires will experience the same force, whether current equal or not. It's similar to the other fields. In magnetic field, force gravitational directly proportional to the product of the masses. In electric field, electric force directly proportional to the product of the charges, and here in the magnetic field, force directly proportional to the product of currents. So this is the similarity. So force in magnetic field depends on the product of the masses, in electric field, product of the charges, and in magnetic product of the currents. So both masses will experience both charges will experience same force, both currents will experience, so whether they are equal or not. And next, look, suppose we have two infinity long wires. This is wire A. It is carrying 1 ampere. Another wire is also infinity long, and it is carrying current 1 ampere. This is B, and both are placed at the distance of 1 meter. Then according to the formula, force per unit length experienced by each is mu naught I1 I2 over 2 pi d. So force per unit length, mu naught is 4 pi into 10 power minus 7. Current is 1, second current 1, 2 pi and d1. So when pi cancel with this, 2 2s are. So the force per unit length will be 2 into 10 power minus 7 Newton per meter. So if the force of attraction or repulsion between two infinity long parallel wires which are unit length apart, mean 1 meter, is 2 into 10 power minus 7 Newton per meter. Then each wire is carrying 1 ampere electric current. And this is the definition of 1 ampere. So electric current unit ampere is defined as if the force of attraction or repulsion between two infinity long wires, parallel wires, which are unit length apart, is 2 into 10 power minus 7 Newton per meter, then each wire is carrying 1 ampere current. Now suppose we have this wire, it is carrying current I1, and according to right hand grip rule, this is the direction of the magnetic field. This is the point P, and the B at P will be mu naught I1 divided by 2 pi d. Now a wire is placed here which is carrying current in the opposite direction. Now this wire will experience force F is equal to mu naught I1 I2 over 2 pi d into L, which can be written as force per unit length, mu naught I1 I2 over 2 pi d. Now the field is in this direction from the current 1. Current is downward. According to Fleming left-hand rule, the wire will experience this direction force. So this is the direction of the force here. Now suppose this red wire is placed here, and we considered its magnetic field around it, and the same distance here, this is the P. Now according to right hand grip rule, this is the direction of the magnetic field. Now at P, the B due to this will be mu naught I2 over 2 pi d. Now we place here the black wire. It was carrying current in this direction. Now the force experienced by this I1 black wire, force per unit length will be mu naught I2 I1 over 2 pi d. Now the force direction, look, this field is going in this direction from the red wire, and the current is up, so force in this direction. So look, right side force on the right wire, left side force on the left wire. It means these two wires will lean outward when the current in the wire is opposite direction. So this is showing the repulsion. So this is the proof that when wires are parallel, carrying current same or different, but in opposite direction, definitely then they will repel each other. But both forces are equal and opposite. Again, Newton's third law is valid, but the force will be repulsive force. When two wires are parallel, carrying current in the same direction, attraction. Opposite direction, repulsion. Similar charges, stationary, repulsion. Similar current means similar direction current, attraction. Opposite direction current wires, repulsion. Opposite stationary charges, attraction. So this is very important. Similar stationary charges will repel. Similar direction current will attract. Opposite stationary charges will attract, but opposite currents, direction current will repel, but the forces will remain same in magnitude, but opposite in direction, obeying Newton's third law. Suppose these are two parallel horizontal wires infinity long and carrying alternating current. So due to alternating current, they will attract, repel, attract, repel. So due to attraction and repulsion, there must be oscillation between the wires. They must oscillate due to attraction, repulsion, attraction, repulsion. Both are attracted, and then repelled, so must be oscillation. But we can't see in the national grid wires, they are horizontal, they are parallel, right? So they are not oscillating. Reason, suppose we assume this wire of the national grid is carrying 500 ampere, which is not possible, right? Suppose this is also the carrying 500 ampere. And the gap between these two wires, suppose in 1 meter. When you will calculate the force of attraction repulsion per unit length, formula will be mu naught I1 I2 over 2 pi d. So the mu naught is 4 pi into 10 power minus 7. This is 500. This is 500 divided by 2 divided by pi d1. This is cancelled. This is 2. So it becomes 5 times 5, 25. 25 multiplied by 2, 50. And with this 10 power plus 4 and then 10 power minus 3. So it is 50 times, sorry, this is minus 7. So minus 7, it is now minus 3 Newton per meter. So it is 50 millinewton force per unit length. Now we have to compare this force per unit length with the weight per unit length. Yes, if the force is greater than the weight of this, then this will be lifted up for the oscillation. So this is the force of attraction repulsion per unit length, millinewton per length. So what is the estimated value of the mass of 1 meter of the wire? Suppose we take this 1 meter wire, maximum 5 kilogram. 1 meter wire of the national grid, 5 kilogram, 10 kilogram. Then what will be the weight? Weight is mg, approximately 5 times 9.81. It's 50 Newton. And here, this is 50 Newton per meter. And look at this. This is just 0.050 Newton per meter. Yes, there is a force of attraction repulsion, but we can't see this vibration. Reason behind that magnetic force of attraction repulsion is very small as compared to their weight. So we can't observe the vibration in the national grid wires.